So we watched the thermite reaction gone wrong last time as part of the safety thing. I wanted you to see what one going right would look like. So this, you can see the reaction takes place. Nobody's by it. Everybody's far away. And you can sort of see going down, it does have, it's really, really bright because the exothermic part of this is very much heat and light. And you can sort of see a stream, if you look careful, coming down. He actually, when they did this one, they double did the flower pots. But on the other guy, he just did one. These flower pots are a lot smaller. He made the reaction a lot smaller. The other guy was trying to make it very big. Everything that they did molten-wise stayed in that container at the bottom, which is filled with sand. So it's all about how you do it and how you approach it. So you can do it safely. It's just a matter of being able to do that. If we go on here, this is a reaction that we used to do. It's called nitrogen triiodide, also known as touch explosive. You actually make the solution up and then you let it dry. They're going to touch it with a feather. You can sort of see the feather shadow coming first. And as they touch it, it is a touch explosive. Since 9/11 because it's considered dangerous. But it was a lot of fun to do. Okay, what type of okay. And this was another one. Remember at the ball we saw last time that glowed white that they did in the experiment that we watched? This is still white phosphorus.
An element dissolved in carbon disulfide is taken into a medicine dropper and used to write on a piece of filter paper.
So it's white phosphorus that's dissolved in carbon disulfide. Now watch what happens. It takes just a few minutes.
As the solvent carbon disulfide evaporates away, the element begins to react with oxygen from the air in a spontaneous exothermic combustion reaction. What is this element?
It's phosphorus. It's pretty awesome. But you have to be really careful with the phosphoruses because they do that. That's what's on your matchstick kind of thing, but it's not the white phosphorus. Okay, so I'm going to go forward here a couple. This is where I want you to grab out your notes. So you got your notes out. Last time we defined exo and endothermic, but I want you to put in there a version of visual, what's going on, okay? So this is a representation of an endothermic process. Endothermic means I'm going to put more heat in it than I get off. Okay, more energy is going in. Huh? In here? Oh, endothermic feels cold to you because it's taking more energy in, yes. Okay, so when I'm talking about bonds, though, it takes more energies to break the bonds in the reactants than it does to form the bonds in the products. Now, try that again. Takes. I always get this mixed up. So endothermic takes energy in and doesn't give it back out. So let's watch this. So I break the bonds. I take a lot of energy, and I make the bonds, and it doesn't take as much energy to make them. So it took more energy to put in to break the bonds than it did at the end when it shows it coming off, but it's actually making them. So I had to put more energy in to make the reaction go. Okay, so would you draw a representation on your notes of what just happened? Okay, I would probably put more energy coming in to break the bonds and then not as much energy needed at the end. This is sort of a little bit backwards. I'll show you the overall reaction that they've got. So again, more energy needed to put in to break the bonds than is needed to when I put my bonds together on the product side. So I'm going to pause the video just for a second so you can, with the thing on. For your lab, you also need to draw an animation of an object that is endothermic, how the heat is going. So this is the back part of your lab, and if you want to do that right now, you can. The next animation I want you to write on your notes is exothermic. Now with exothermic, we need energy to break bonds. We always have to have energy to break the bonds. So we're going to put some energy in to break the bonds. It doesn't take as much energy there as is what is given off when the bonds come together. Okay? So the overall reaction for an exothermic says, I don't need much energy to break the bonds, but when I put the bonds back together, they have excess energy that they give off. Okay? So we get an exothermic reaction. So on the product side, I end up with extra energy. That can be given off in light, in heat, in any of the ways that we talked about last time. So sound, electric, any of those. And then when you get done with this, look at the back of your lab, and that bottom one's supposed to be draw an animation of an exothermic reaction. Just use an object again, don't necessarily draw this. In fact, I don't want you to draw this animation here. I want you to draw your own, just an object. You decide what the object is, and then show me where the heat is going in an exothermic reaction. Is it coming off of it, going into it, surrounding it? What's happening to it? After drawing, then you can finish it in lab or after the lab as you finish. So what we're going to be doing is an endo-exothermic lab, a very basic thing. We're going to classify chemical reactions as endo and endothermic based on loss or gain of heat. So really quickly, define exo and endothermic right there in words that you understand. So really quickly write down just what is exo and what is endo. What does it mean?